Okay, so as you mentioned, my name is Phoebe Unger, and I go to Washington State University, and my advisor is Dr. Minto Michael. My project is on the rapid identification of Listeria monocytogenes and Escherichia coli 0157H7 in milk and cheese using hyperspectral imaging. So just kind of an outline of what I'm going to go over. First, kind of the need for the technology, then the concept behind it, some of the advantages and disadvantages, and then the start of our research so far. So for the need, according to the CDC, roughly about 1 in 6 Americans get sick from foodborne illnesses each year. And this results in about 128,000 hospitalized and about 3,000 deaths. Two of the main contributors to this is Escherichia coli 0157H7, which is one of the top 5 foodborne pathogens resulting in hospitalizations. And then Listeria monocytogenes, which is one of the top 5 foodborne illnesses that results in death. And these are both pathogens found in dairy products and within the dairy industry. So in order to test to see if these are in our products, we need detection methods. So there's traditional methods, which are often laborious and time-consuming and often are culture-dependent. So it could take several weeks to possibly get a positive or negative result. And then we also have rapid methods, which are faster, more convenient, more sensitive, and more specific. And these often rely on physical, chemical, immunological, and molecular principles. And this is kind of where hyperspectral imaging fits in. It's an emerging rapid detection method. So the history behind hyperspectral imaging, the term was first coined by Goetz et al. In 1985 when they were using it for remote sensing to map an Arizonian desert. And this is just kind of the idea behind it here. So they have a satellite which would have the hyperspectral imaging software programs and stuff. And then they have a light source, which is the sun, which would emit rays down to the surfaces below, such as water, grass, and soil. And then these would reflect different wavelengths back to the satellite and the camera. From this remote sensing, it's also been found in other fields such as astronomy, agriculture, pharmaceuticals, and in medicine. So what exactly is hyperspectral imaging? It's a combination of conventional imaging and spectroscopy. Conventional imaging offers the position of a sample and kind of where things are in relation to each other. And this is often referred to as spatial information. And then we have spectroscopy, which offers the light absorption of a sample, which is spectral information. And as you can kind of see from the chart here, spectroscopy and conventional imaging are both great technology separately, but when combined together within hyperspectral imaging, you kind of get the best of both worlds, plus a little bit more, such as the flexibility of spectral extraction. So a common setup, which you'd find in a lab, often consists of a camera connected to a spectrometer, and this would be connected to a computer to store, save, and later on analyze the data. And then you need a sample stage, which can be modal or stationary, depending on what you're doing. And then you also need a light source. And where the light source is kind of depends on what type of hyperspectral imaging you're doing. So if it's reflective hyperspectral imaging, the light would be kind of off to the side. If it's transmittance, it would be below the sample, so it would transmit through to this camera and the spectroscometer. And then you also have the option of adding a microscope. And this is basically if the subject in question is not visible to the naked eye and needs to be enhanced. So kind of the concept of what you get from an image, it's called a data cube or a hypercube. And it's basically, as the name suggests, it has 3 dimensions, 2 spatial and 1 spectral. So the 2 spatial are the X and the Y position you see on this picture here. And then you have the 1 spectral of the wavelength, they're often referred to as the gamma dimension. And this cube is basically a series of subcontinuous images, and you can pull a whole bunch of different data from it. So you could do a bandpass, which is the entire image at a certain wavelength, or you can look at a pixel at a whole range of wavelengths to identify chemical composition. So some of the advantages of this technology is there's very little sample preparation that is actually required. It also is a relatively chemical-free assessment method, so you don't have to worry about harmful chemicals, teaching workers, and then having to dispose of them. It's also rather simple and quick once it's calibrated and validated. You have to make sure what you are looking at is exactly what you're looking at. It also is a non-invasive and non-destructive method, so you're not wasting a whole bunch of sample and then in turn losing profit. And then it also helps you collect a complete spectrum of data, so you have a large amount of data to choose from later on. And then you also can help determine several constituents within the same sample. And this is basically saying you're not just testing for Listeria, for example. You could pick up Listeria or E. coli, and you're not going to be missing a potential pathogen. And then also, it'll eventually become economical. It is a large startup cost, but the main part of my project is finding a more affordable option using just a microscope and a hyperspectral imaging camera. And then so some of the disadvantages is, like I said, you can get a substantial amount of data, but with the right analyzing software, you can actually mine the information you're looking for fairly easily. And then it also has a substantial startup cost, but like I said, it will pay for itself. There's not a whole bunch of disposable parts, so you're not having to re-buy new parts to it. Also, the calibration can be time consuming, but almost any lab technology is. So you make sure you actually are getting the results you think you're getting. And also the object of interest must have different diagnostic absorption features. So this is basically saying E. coli and Listeria can't have the same spectrograph, or else you wouldn't be able to tell the difference between the two. So for our research, we're just getting started due to the whole COVID thing, but our objectives were to develop an affordable hyperspectral imaging system using just a regular compound microscope and then a hyperspectral imaging camera that's just connected to an everyday computer like a laptop. And then once we get this set up, we're going to evaluate the efficacy of hyperspectral imaging to identify single and mixed strains of Listeria monocytogenes and Escherichia coli 0157H7 in growth media. And then we're going to take this one step farther and apply it to dairy products such as whole milk and in cottage cheese. So far in our research, we've received the hyperspectral imaging camera and determined the best way to actually mount the camera onto the regular compound microscope. We also began to investigate some of the ideal settings for the microscope and the camera and the software for actually capturing the images so we get clear, readable images. We also purchased and began to explore our analyzing hyperspectral imaging software, which is Environment for Visualizing Images, or ENVI. And we've explored some of the techniques for actually preparing the samples to be examined and worked on the protocol for actually capturing some of these images. So this is just kind of an example of the setup we have. It's just an everyday laptop, and then we have an Eagle Eye hyperspectral imaging camera, which is the blue piece that is connected to the microscope. And this is connected through the computer with just a simple USB. And then we also have a normal compound microscope, which you'd find in any micro lab. And then the part you can't actually really see here is the analyzing software, which is the Environment for Visualizing Images, or ENVI, which is just downloaded onto the computer. So this is just an example of what an image would kind of look like. It has not been analyzed. So on the right is a conventional image of some lactic acid bacteria that is just from a microscope. And then on the left, we have the hyperspectral image. And as you can see the unique parts that were on the conventional images. There is a little bit different coloring and a little bit magnification, but this is still a work in progress right now. We're still working on fine-tuning the images. So kind of going forward, we're going to continue fine-tuning the images and the settings for actually capturing the images, finalize the protocol for actually preparing the samples so they're prepared the same way every time, and then develop a method for analyzing the samples on the ENVI software. And then we'll determine actually the hyperspectral signatures for the organisms in questions. And this is basically making a library. So when we do samples, we do have a baseline to compare it to. And then we'll also then evaluate the efficacy of hyperspectral imaging to detect single and mixed strains of Listeria monocytogenes and Escherichia coli in the growth media. And then, as I said before, the dairy products such as milk and cottage cheese.